Power Electronics Research Centre comprises 7 researchers working in the general area of magnetic component design and power electronics. The applications would range from high power applications such as in renewable energy systems down to energy harvesting and magnetics on silicon for power supply on chip. Okay. So most of my research today has focused on planar magnetics, where the aim is to miniaturize the magnetic components for portable mobile applications. So the types of technologies I've worked with would be PCB magnetics, thick film magnetics, and then thin film on silicon, which is related to the power supply on chip. So with current technologies, the power supply consists of lots of components being added to the silicon, and the ultimate goal is to integrate all of those components within the silicon technology itself, and that would include the magnetic components. We've worked with Tyndall on magnetics on silicon before, where we were designing racetrack inductors, but we identified that there were some issues. When we want to go to higher power levels, we're limited in terms of the current handling, and also because of saturation in the magnetic cores, it limits the power levels that can be applied. So there has been a move to use coupled strip-line inductors on silicon, and that's where this project focused. In our designs of racetrack inductors, we found that by dividing the racetrack inductor up into one big one into several smaller ones, we could gain advantages in terms of the utilization of the magnetic material, and also it provided opportunity to switch some of the parallel paths out as power levels reduced, and that would be important in mobile applications where your device is spending a lot of time in low power mode when you're not using it, so when it's in your pocket or in your bag, when it's in sleep mode. With mobile applications demanding increased functionality, there's a corresponding increase in the power that these devices need. And from our previous work, we identified that the magnetics on silicon are limited because of the small size of the conductors. They're limited in terms of the current handling, and they're also limited because of saturation of the magnetic core regions. So to overcome those issues, coupled strip-line inductors are being investigated.
So by distributing coupled inductors in parallel, we're able to improve the utilization of the core material. Also, by distributing them in parallel, we're able to add additional flexibility to our system. So during periods of light load operation, such as sleep mode, we're able to switch out parallel coupled inductors to improve the efficiency over a load range. So through the National Access Programme in collaboration with Tyndall, we were able to develop models to optimize the structure of coupled strip-line inductors using their technology.
The most common approach to modelling of coupled inductors to date is finite element analysis. However, that tends to be expensive and time-consuming. So the main output of this project is a complete analytic model for coupled inductors that can be programmed in standard mathematical software.
So the models developed during NAP have been validated using finite element analysis and measurements, and a number of publications have been submitted. So under test here, we have a DC to DC converter capable of supplying 2.6 amps. We can see here that we're using the 5-phase coupled inductor fabricated by Tyndall. So here we have a three-dimensional finite element analysis model used to validate our analytical models.
The ICT for Energy Efficiency group at Tyndall National Institute is widely recognized as world leaders in the area of integrated magnetics for power supply on chip. And through the NAP project, we've worked closely with the Power Electronics Research Group in National University of Ireland, Galway, Dr. Maeve Duffy's team there, who are experts in circuit topology and design of different power circuits. And that, coupled with our expertise in magnetic passive components, we were able to come up with a novel solution for addressing the challenging challenging topic of microprocessor power delivery. Within the project, we designed and optimized the coupled inductor structure for a 3-phase and 5-phase circuit, and we worked with Dr. Maeve Duffy's team in optimizing the power circuit required to address this challenge. Once we had the optimized structure finalized, these devices were fabricated at the MEMS fabrication facility here at Tyndall, which is state-of-the-art. And the fabricated devices were tested initially for die-level performance, and then they were packaged along with the power circuit that Dr. Maeve's team had developed. And then the final full circuit testing was done in Galway, and the results were very encouraging. And we managed to show an efficiency of 86% for the coupled inductors for the 3-phase and 5-phase, which is the highest reported in literature.
The devices that have been designed here using our analytical optimization in-house tool were characterized with one-port impedance measurement. Measurements were done with the frequency and bias width. We have also more advanced characterization equipment where we can measure end-port devices to determine precisely coupling, leakage and other circuit parameters.